21 ECC 202T Analog and Linear Electronic Circuits. Unit 3 Oscillators, Principles of Oscillation, Classification of Oscillators, RC, LC and Crystal Oscillators. Principles for Oscillation. An oscillator is an electronic circuit that produces periodic signals without requiring an external input signal. In feedback oscillators, a portion of the output is fed back to the input in phase with the original signal. This positive feedback reinforces the signal and maintains oscillations. For stable and undistorted sine wave generation, the overall loop gain should be equal to 1. If the loop gain becomes greater than unity, the amplitude increases and distortion occurs. If the loop gain is less than unity, the oscillations gradually die out. Feedback oscillators are widely used in communication systems, signal generators, and electronic instruments. The feedback oscillator configuration is shown in the figure. The amplifier has a gain A and the feedback network is having a gain beta. For an oscillator to produce continuous oscillation, certain conditions must be satisfied. First condition is Barkhausen criterion. According to Barkhausen criterion, the loop gain A beta must be unity or slightly greater than 1. If the loop gain is less than 1, the oscillations gradually decay. If the loop gain is much greater than 1, the output amplitude increases excessively and causes distortion. The total phase shift around the feedback loop must be 0, 360, 720 and so on, so that the feedback signal remains in phase with the input signal. When both magnitude and phase conditions are satisfied, stable sinusoidal oscillations are obtained. Next we are going to look into RC phase shift oscillator. The RC phase shift oscillator circuit diagram is as shown in the figure. It has an op-amp and 3 RC networks. An RC phase shift oscillator generates sinusoidal signals using a combination of op-amp amplifier and an RC feedback network. The op-amp is connected in the inverting mode, which inherently introduces a phase shift of 180 between input and output. The network means the feedback network usually contains 3 RC stages connected in series. At the oscillation frequency, each RC stage contributes approximately 60-degree phase shift. Therefore, the total phase shift becomes 180 degree. Combined with the 180 phase shift of the inverting amplifier, the overall phase shift becomes 360 degree, satisfying the Barkhausen criteria. The RC network also determines the frequency of oscillation. RC phase shift oscillators are commonly used for generating low frequency sine waves. We can analyze the RC feedback network and we can derive the expression for frequency of oscillation using mesh current analysis. So, by considering the RC feedback network, we have 3 loops. So, 3 loop currents I1, I2, I3 are assumed in the cascaded RC network. By applying KVL to each loop, the mesh equations are obtained as follows. Loop 1, the mesh equation is I1 into R plus 1 by SC minus I2 into R is equal to V out. Loop 2, minus I1 R plus I2 into 2R plus 1 by SC minus I3 into R is equal to 0. And for loop 3, minus I2 into R plus I3 into 2R plus 1 by SC equal to 0. The feedback voltage can be obtained as Vf is equal to I3 into R. Here 1 by SC is the capacitor impedance, that is ZC. So the mesh equations are solved to determine the current flowing through the final RC section. So from I3 we can calculate the feedback voltage Vf also. So here Vf equal to I3 into R. By solving the mesh current equations, we can get I3 is equal to V0 R square S square C cube, V0 R square S cube C cube divided by 1 plus 5 SRC plus 6 S square C square R square plus S cube C cube R cube. So the feedback voltage can be written as I3 into R, that is equal to V0 R cube S cube C cube divided by 1 plus 5 SRC plus 6 S square C square R square plus S cube C cube R cube. Next we are going to see beta, that is the feedback factor. Beta is given as 1 by 1 plus 6 by SRC plus 5 by S square C square R square plus 1 by S cube C cube R cube. By substituting S equal to j omega, we can get S equal to j omega, S square equal to minus omega square, S cube equal to minus j omega cube. Thus, beta becomes 1 by 1 minus 5 alpha square plus j alpha into alpha square minus 6, where alpha is equal to 1 by omega RC. The parameter alpha is introduced to simplify the mathematical expression of feedback factor. For oscillation to occur, the Barkhausen criteria requires the loop gain A beta to be unity and the phase shift to be 0 or 360. So, we are considering A beta equal to 1. Therefore, the feedback factor beta must be purely real. Hence, the imaginary part of the feedback equation is equated to 0. So, from the imaginary term, we can get alpha into alpha square minus 6 equal to 0. So, alpha square will be equal to 6 and alpha becomes root 6. By substituting this value in our alpha original equation, we can get 1 by omega RC equal to root 6. So, omega equal to 2 pi f. So, we can find out f, that is the frequency of oscillation, f0 equal to 1 by 2 pi RC into root 6. So, the frequency of oscillation for the RC phase shift oscillator is given as f is equal to 1 by 2 pi RC root 6. The feedback factor at the oscillation frequency, we can get beta is equal to minus 1 by 29. In RC phase shift oscillator, the RC network attenuates the signal by a factor 1 by 29. To satisfy the Barkhausen criteria, A beta must be equal to 1. So, the amplifier must provide a minimum gain of 29. So, for an inverting op-amp configuration, the gain is given by A is equal to minus RF by R1. Hence, we can find out the feedback resistor and the R1 relationship. So, the feedback resistor must be approximately 29 times the input resistance. Practically, the gain is set slightly higher than 29 to ensure reliable startup of oscillations even when component values vary due to tolerances or temperature changes. If the gain falls below the required value, the oscillations lose energy and eventually stops. The 741 op-amp is suitable for low frequency oscillators because of its limited bandwidth and slew rate. For higher frequencies, faster op-amps like LM318 and LF351 are used to maintain stable and distortion-free oscillations. Next, we are going to analyze the Wien bridge oscillator. The Wien bridge oscillator is commonly used to generate low distortion sine wave signals in the audio frequency range. In this circuit, the feedback signal is applied to the non-inverting terminal of the op-amp. Therefore, the op-amp works as a non-inverting amplifier. A non-inverting amplifier does not produce a 180-degree phase shift between input and output. Hence, the feedback network is not required to provide any additional phase reversal. The Wien bridge network acts as a frequency selective positive feedback circuit. At the oscillation frequency, the phase shift of the feedback network is 0, satisfying the phase condition for oscillation. The oscillator produces stable and low distortion sinusoidal output signals. It is widely used in audio generators, signal generators, and instrumentation circuits. The Wien bridge oscillator circuit is shown in figure A, and figure 2 depicts the bridge configuration of the Wien bridge oscillator. So the figure 1 Wien bridge oscillator using an op-amp in non-inverting configuration, the series RC network R1C1 and parallel RC network R2C2 form the Wien bridge feedback network. The output signal V out is fed back to the point A, and the feedback voltage Vf developed across the parallel RC branch is applied to the non-inverting input terminal of the op-amp. In figure 2, the equivalent Wien bridge network representation is shown. The bridge consists of a series RC arm R1C1, a parallel RC arm R2 parallel C2, and two resistive arms RF and R1. At balance condition, the bridge provides zero phase shift, satisfying the Barkhausen criterion for sustained oscillations. Next, we are going to derive the frequency of oscillation for the Wien bridge oscillators. So the gain of the amplifier depends on the feedback resistor RF and resistor R3. So the feedback factor beta represents the fraction of the output signal that is fed back to the input. To determine beta, the RC network is analyzed using impedance concept. Z1 represents the impedance of the series RC branch, while Z2 represents the impedance of the parallel RC branch. We can calculate the frequency by following the below given steps. The gain of the op-amp amplifier is given by A is equal to 1 plus RF by R3. The feedback factor of the RC network can be found out by beta is equal to Vf by Vo, that is equal to Z2 by Z1 plus Z2. The impedance of RC networks are Z1 equal to R1 plus 1 by SC1, which is equal to SR1C1 plus 1 by SC1. Z2 equal to R2 by 1 plus SR2C2. The feedback factor beta of the RC network is expressed as J omega R2C1 by 1 plus J omega R1C1 plus R2C2 plus R2C1 minus omega square R1R2C1C2. For the beta to be real quantity, the imaginary part must be equated to 0. So 1 minus omega square R1 R2 C1 C2 is equal to 0. So we can find out the F0 from the omega value. So F0 will be equal to 1 by 2 pi root of R1 R2 C1 C2, where F0 is the frequency of the oscillation. If we consider R1 equal to R2 and C1 equal to C2 equal to C, so we can get the F0, that is the frequency of oscillation, equal to 1 by 2 pi RC. The feedback factor becomes beta equal to 1 by 3. For sustained oscillations, A beta must be greater than or equal to 1. So that means A must be greater than or equal to 3. So for a non-inverting amplifier, the gain of the amplifier A is given as 1 plus Rf by R1. So 3 will be equal to 1 plus Rf by R1. So Rf will be equal to 2 R1. RC oscillators using op-amps are mainly used for low and medium frequency applications. Typically, these oscillators operate effectively in the range of 10 Hz to 100 kHz and in some cases up to 1 MHz. To obtain very low frequencies, large resistor and capacitor values are required, making the circuit bulky and impractical. Therefore, the minimum operating frequency is limited by the physical size, the availability of passive components, etc. At high frequencies, the op-amp performance becomes limited due to bandwidth and slew rate restrictions. Because of these limitations, RC oscillators are not preferred for RF or very high frequency applications. High frequency oscillators are generally implemented using BJTs combined with LC tuned circuits or crystal oscillators for better stability and performance. Next we are going to see some problems on RC phase shift oscillator and Wien bridge oscillator. Let's see the first problem on RC phase shift oscillator. An RC phase shift oscillator uses three identical RC sections with R is equal to 10 kilo ohm and C equal to 0.01 microfarad. Find the frequency of oscillation. So the frequency of oscillation for an RC phase shift oscillator is given as FO equal to 1 by 2 pi RC root 6. By substituting the value of R and C, we can get F0 equal to 1 by 2 pi 10 into 10 to the power 3 into 0.01 into 10 to the power minus 6 into root 6, which gives F0 equal to 650 Hz. So we can get the frequency of oscillation is approximately equal to 650 Hz. Next problem. A Wien bridge oscillator is designed to operate at 5 kHz. If C equal to 0.005 microfarad, find the value of resistance. For a Wien bridge oscillator, we have the frequency of oscillation equal to 1 by 2 pi RC. From that we can find out R is equal to 1 by 2 pi FC. By substituting the value of F and C, we can get the R is equal to 1 by 2 pi 5000 into 0.005 into 10 to the power minus 6. So R can be approximately equal to 6.37 kilo ohm. Thank you.